Reactions in aqueous solution. We're going to look at ionic equations. In this example, reaction, I have given you the state of matter, whether it's aqueous, which means dissolved in water, or solid. For the complete ionic equation, everything that is aqueous breaks apart when we put it into water. So silver nitrate is aqueous. When I put that in water, it breaks apart into Ag plus and NO3 minus ions. NaCl is aqueous. When I put that in water, it breaks apart into Na plus and Cl minus ions. On the product side, AgCl is a solid. We're going to keep that together. We do nothing to solids. But NaNO3 is aqueous, so break that apart into ions, Na plus and NO3 minus. What you'll notice is that NO3 is aqueous on both sides. Na plus is aqueous on both sides of the equation. Those are called spectator ions. Spectator ions are not involved in the reaction. The net ionic equation gets rid of the spectator ions. So for this example, when I get rid of those spectators, my net looks like this. The net ionic equation shows the formation of the solid AgCl. Let's look at another example. Now when you have ionic equations, it's best, although there are a couple ways to do this, it's best to balance before you start. So in this example, I'm going to add coefficients to balance the equation before I start. Then I'm going to write the ionic equation. Lead is a solid. Keep it like it is, write an S after the symbol. AgNO3 is aqueous, which means we're going to split apart into ions, 2 Ag plus and 2 NO3 minus because of the coefficient. On the product side, silver is a solid, keep the S after it, and lead nitrate is aqueous, so break that apart into ions, Pb plus 2 and 2 NO3 minus. Now if it's aqueous, it's important to keep these charges up here. That indicates that it's aqueous. Spectator ions, well there's only one in this case, and that's 2 NO3 minus. It's aqueous here, it's aqueous here, that's a spectator. The net ionic equation shows lead going from a solid to aqueous and silver going from aqueous to solid. So what I have underlined is the net ionic equation. So how do you know if something is a solid or aqueous? You know the solubility rules. If it says soluble, it's aqueous. It will dissolve in water. If it says insoluble, it's a solid. It will form a precipitate. So you need to know the solubility rules in order to determine whether you're going to get a solid or not. Let's look at a couple examples, and I've kind of skipped around on your notes so you can find the appropriate examples. Before you start, on part A here, go back and balance the equation. Put a 3 in front of NaCl to balance. We want a net ionic equation. So if it's aqueous, we're going to split it apart. Na3PO4, aqueous. The ions, there are 3 Na plus ions, plus a PO4 ion with a negative 3 charge. FeCl3 is aqueous. Split it apart into ions. Fe has a plus 3 charge here. Plus, there are 3 Cl minus ions. On the product side, NaCl is aqueous. Split it apart into ions. 3 Na plus and 3 Cl minus. FePO4 is a solid. Keep it together. Don't do anything to the solid. Spectators. Na plus is aqueous on both sides. Cross it out. Chloride is aqueous on both sides. Cross it out. The balanced net ionic equation is PO4 with a negative 3 plus Fe with a plus 3 forms the solid FePO4. In this next example, Na3PO4 plus CrCl3. I didn't give you the products, but it's a double replacement reaction, so sodium and chromium will switch. So sodium will combine with chlorine, and the charges are +1 and -1, so NaCl. Chromium will combine with PO4. Chromium is a +3, PO4 is a -3, so CrPO4. I have to determine which one of these products is the solid, so you go back to your solubility rules. Anything with sodium is aqueous. Phosphates are mostly insoluble, so there's my solid. I've got the products. I need to balance it before I continue. So balance it with a coefficient of 3, and then we're going to write the complete ionic equation. If it's aqueous, break it apart into ions. So Na3PO4 is aqueous. And again, write the charges if it's aqueous, +1, -3. CrCl3 is aqueous. Break that apart into ions and write the charges. NaCl is aqueous. Split that apart into ions. And then CrPO4 is a solid. We do absolutely nothing to the solid. Cross out the spectator ions, those that do not change. Na+ is aqueous on both sides. Cl- is aqueous on both sides. So I'm underlining the net ionic equation. Number 2, will a precipitate form when you mix solutions of these compounds? I'm going to predict the products first of all. The positives are going to switch, so silver is going to combine with SO4 to give me Ag2SO4. And sodium is going to combine with NO3 to give me NaNO3. Will a solid form? So I go back to my chart and determine whether these are aqueous or a solid. Ag2SO4. Sulfate salts are soluble, but silver is an exception. So this is a solid. It is insoluble. NaNO3, anything with NO3, is aqueous. So will a precipitate form? Yes. Ag2SO4 is a precipitate. It's a solid. And you can only get one solid. You can't get two solids with the products. Look at this second example. Again, I want to predict the products. So NH4 and barium switch. NH4 combines with NO3. Now charge-wise, you've got +1, -1. So that's my product. Plus barium with chloride. Barium's a +2, chlorine's a -1, so BaCl2. Go back to the chart. Anything with NO3 is aqueous. Chloride salts are soluble. There are some exceptions, but barium is not one of the exceptions, so BaCl2, according to your chart, is also aqueous. So will a precipitate form? In this case, no. No solid is formed. Let me do one more. CaCl2 plus K2SO4. Calcium will combine with SO4. And then you're going to get potassium with chloride. Go back to the chart. CaSO4, that's a sulfate salt. Sulfate salts are soluble, but calcium is an exception. So this is insoluble. It does form a solid. Anything with an alkali metal is aqueous. Potassium is an alkali metal. It's group 1A, so that's aqueous. So will a solid form? Yes. Calcium sulfate.